Hi, welcome to Unit 3. Can you believe it? Unit 3 already. Well, Unit 2 sure was a long one, wasn't it? But I'm happy to say most of the rest of our units are going to be quite a bit smaller, and none of them will be as long as that one. But it's really important that we get through those fundamentals so we can get to some new stuff. So this will be just a little bit more review, but in this unit we're going to start really starting to break in to that Algebra 2 curriculum. So let's take a look. Unit 3 is all about systems of linear equations. Today we're going to look at solving systems of linear equations graphically. I bet you can guess what goes in these blanks, right? Let's fill them together. A system of linear equations includes two or more linear equations. A solution to a system of linear equations is an ordered pair that is a solution to all the equations in the system. Let's take a look at this first system of equations. It is a system of linear equations, first of all, because there are two of them. And they are linear because all the variables are to the first power. Let's graph this first one. Y equals negative 3x minus 1. That's a line, the y-intercept at negative 1, and a slope of down 3 to the right 1. I think I'll go ahead and use that to kind of get it started. Well, might want to. Oops. There we go. What do you think about that? Does that look pretty accurate? I think that's good. Okay, next. Let's graph the other one. This other one now, this is in standard form, so we could get the x and y intercepts, couldn't we? The x-intercept, if we put a 0 in for y, we just have to solve this equation here. That's x equals negative 2. The y-intercept, we put a 0 in for x, and we just solve this, we get y is equal to 4. And now I can draw the line through there. Okay, it appears as if these two equations do have a solution in common. The solution that they have in common is the point where they intersect. Negative 1, comma 2. But let's not take it for granted. Let's check our work. So first I'm going to make sure that negative 1, 2 is a solution to the top equation. If it is, then this should be a true statement. Does 2 equal, let's see here, negative 3 times negative 1 is a positive 3? Yeah, that's definitely true. All right, now we'll try the bottom equation. Put a negative 1 for x, a positive 2 for y. And this is supposed to equal negative 8. So it's a negative 4 minus 4. Well, that does equal negative 8. So we found that this point is a solution to both equations. Remember, a solution is a value that when you plug in the x and y values, a solution is a point where you plug in the x and y values, it gets a true statement. All right, let's try this next one. Ooh, we got point slope form, my favorite. All right, so let's plot the point 1 comma negative 4. It's always opposite the number with x, opposite the number with y. So 1, negative 4. The slope is 2, so we'll be going up 2 over 1 from there. Just like that. I'll draw a line through there. All right, super. All right, let's try the next one. All right, I've got 2x minus y is equal to 4. Well, let's see here. We can get the x-intercept. The x-intercept is 2, right? And the y-intercept, if I solve negative y equals 4, I get y equals negative 4. And we can draw the line through there. You'll notice that it's the same slope of up 2 over 1. And we could confirm that by solving this for y. These two lines are parallel because they have the same slope. We've already learned that. Since they're parallel, they never intersect. So there is no solution to this system of inequalities because there's no point that's on both lines at the same time. All right, you've got a couple practice problems, so pause the video and give them a shot, please, and then we'll go over your work. All right, for the first one here, I've got point slope form. I'm going through the point 2, 3 with a slope of -4. So down 1, 2, 3, 4, and to the right 1. And I'll draw a line through there. Super. All right, next we have the x plus 4y equals -1. Don't think I want to try and use like the intercepts there. I think I just want to solve this. And so I'll get y is equal to a -1 over 4x minus a 1 over 4. Okay, well, we solved it for y, and this is a pretty ugly y-intercept for me to start my process of using the slope. So I think I might try a little different strategy. Can you see what the x-intercept here is of x plus 4y equals -1? The y-intercept is -1/4, but I think if you plug in a 0 for y, you'll agree with me that the x-intercept is a -1. So I want to have a point that I can start my slope process at, but I want to use -1, not -1/4. Then I'm going to go down 1 over 4. 1, 2, 3, 4, which is absolutely perfect. So that the kind of the moral of the story there is you don't have to start at the y-intercept. You try and put in slope-intercept form if the y-intercept's ugly, find a different point. Find one that starts on the lattice where the little grid matches up. I think we agree now that this point must be 3, -1. That's the solution. We could plug them in and check. I'll leave that to you to check, but it's definitely right. All right. Let's see how we did on the next one. Y equals 5x minus 6. Okay, this is a little more straightforward. Got -6 for a y-intercept with a slope of 5. So we're going to count up 5 over 1. Maybe do that a couple times. And we'll draw the line through. Okay. We got y plus x equals 0. I'm going to solve that one for y. Just say it's y equals -x, which is going to go right through the origin with a slope of down 1 over 1. I think we already see what the point's going to be. Let me just connect away. So 1, -1 is our solution, and that definitely works. Let's try the next one. Point slope form. Your friend and mine, point slope form. We're at a point. This point here is -3, 1. So I'm going to start at -3, 1. I'm not saying that's my solution. It's just a point I'm starting at. And I'm going to slope it down 1 over 2. All right, I think I've got the story going there. All right. Our next one is x plus 2y equals -1. X-intercept is going to be a -1 when you plug in a 0 for y. It's going to be kind of ugly to solve this, but this will help me get the slope. So I don't like that y-intercept. I much prefer the x-intercept at -1. And then we'll graph that with a slope of down 1 over 2. What do you notice? What do you notice? This is the same line, y'all. So this graph is the same line twice. And what we say there is we say that this is infinitely many solutions. Now, please don't misunderstand me. I am not saying that all real numbers are solutions. Not at all. I'm saying there's an infinite number of points since they lie on the same line, but it's only the points that are on these lines that are solutions. Systems of linear equations can be classified by the number of solutions. We have an independent system with one solution, an inconsistent with no solutions, or a dependent system that has infinitely many. So if a solution is independent, that means we have two distinct lines that are intersecting at one point. Something like that, maybe. An inconsistent system is one where you have two parallel lines. And a dependent system is where the lines are the same. Or at least that's what they look like when we're dealing with linear equations of two variables. This kind of vocabulary becomes very important in later, higher level math courses, but for us, there's just good to start getting used to using these ideas that independent has one solution. And the way I remember that is that if you're an independent person, you are one of a kind, right? If you're inconsistent, I can't rely on you for anything. So I can't rely on you to get a solution. And if you're dependent, that means you always want to be like everybody else. You're just dependent on everyone else. So it's infinitely many. That's nothing mathematical there. That's not why that's called that, but that's a good way to remember it for me. All right, last, I want you to, let's write down some vocabulary here. In order for a system of two linear equations to be independent, in other words, they have to have one solution, the two lines must have what? What do we notice? If they're going to be parallel, they'd have to have the same slope. And if they're going to be the same line, they have the same slope. But if they have a different slope, we know that they have to intersect somewhere. So the two lines must have different slopes. So with that in mind, I bet you could identify from looking at these which one of these are going to be independent. So without graphing, identify which one of these is an independent system, meaning they have one solution. Pause the video and do it. Okay, so for this one here, you notice that the ratio of the x's to the y's is the same. That's because they have the same slope. They have a slope of 5/2. So this is not independent. Now, whether they're the same line or parallel lines would take a little bit more work. If we look at the constant here of 12 and 8, these are all double these, so this would be parallel. This would have to be a 16 for them to be the same line. Looking here, the slopes are given to us right there. These are not the same slopes, so these are independent. They must intersect somewhere. What about here? Well, these are clearly, this is a slope of actually -3. This is a slope of 2. These are clearly independent. And what about this? Well, let's see here. 2/3. If I subtract over the x over here, I have a funny feeling. If I divide both sides by 3, a -2 divided by a -3, that is the same slope. So these are not independent. They do not have one solution. Are they the same line or are they parallel? We'd have to do some more work to figure that out. And I'm not sure, and I'm not going to figure it out. So that's the answer. All right, for lesson 1, I want you to write, for your x, to write 3 systems of equations, one that's independent, one that's dependent, and one that's inconsistent. You could do this very easily, or you could actually try and make these problems somewhat interesting. I'll leave that up to you. So until next time, take care.